I'm really happy to be here because it's my first presentation for Ukrainian team for a long time, especially since I moved to Switzerland. And today I will talk about the things that I work on every day. This is a static Kotlin bug hunting. So basically how you write static analysis for languages and especially Kotlin. So, before we start, let me introduce myself. For those who don't know me, I am a software engineer at Sonar, and I also speak at some conferences. I organized some conferences in my past, like a lot of programming languages like Java, Kotlin, Scala. I had some romance with TypeScript as well. And this is my Twitter handle, so you can follow me if you want. And there is one more important thing that you should know about me. I am Ukrainian. I was born and raised in Kiev, and I live in Switzerland only for 2.5 years. And in order for people to understand this, I have these nails in the color of Ukrainian flag. So you can see my message to Russian worship can be even stronger. And usually after this slide, I share the link with some foundation like Save Life in UA for people from Europe. And here I know that you're already donating for Ukrainian kids. So thank you for this. We really appreciate this. And Slava Ukraini. Let's start. What are we going to talk about today? Today I'll show a little bit about the history of static analysis in our company. Then we'll talk about the why, what was wrong with Kotlin, and why we needed sort of a Sonar Kotlin 2.0. Then we'll talk about the feedback that we received after first releases, and a little bit about achievements and the takeaways. So this is how the report of SonarCube looks in the previous LTS, which is 8.9, for some ordinary Kotlin project. So you can see there are 64 bugs, for around 400 code smells, and there is 4 days and 6 hours of technical debt. Then, if we take exactly the same project but analyze it with the latest LTS, which is SonarCube 9.9, you'll see that the technical debt became almost a month. There are 3 times more bugs. There are vulnerabilities that were not present before, and there are 2 times more code smells. So for some people, it might seem that my job is to make your code base worse. But that's actually not true. The code is the same. It's that our analyzer became more mature and started finding more and more interesting things to make your code even better. So we can help you make your code better. So what happened between these 2 releases? In order to understand completely what happened, let's forward to the past and see how it was and what's now. So history. How static code analysis works in general. Usually you have some source code. For example, let's have some class hello world with some function. Then using compiler frontend, we are transforming it into abstract syntax tree. So you can see this is a tree with some functions, blocks, call expressions, and so on. This tree looks pretty complex, and I'll have to refer to it many times in this presentation. So let's just show a tree instead. Every time you see this tree, it's basically abstract syntax tree. And then we run some checks, so write some like inspections on top of this tree, find some patterns, and generate a result for you. For example, here you have unused variable. This code can be refactored because it's dead. Here you have a to-do comment, and so on. And a lot of other interesting findings. So the in general scheme looks like this. We have a source code, transform it into the tree, and then we generate the result. Some time ago, in Sonar, we find out that there is a problem here. The problem is that for every language, and we have around 30 at the moment, tree looks different. Trees are completely different, and it means that we have to write exactly the same checks, but 30 times, which sounded like not really optimal. So there was an idea that maybe we can have one tree to rule them all. So maybe we can have some intermediate representation, run all the checks on this intermediate representation, and then we can have the rule or write the rule only once and have it immediately in all the languages. So this was actually implemented and worked approximately like this. You still have your source code, we still generate abstract syntax tree for your native language, and then we transform it to some intermediate tree representation and run the checks on top of that intermediate tree. So, and then you have the result. This technology is working, is open sourced, and for some time there were 4 languages built on top of this technology. It was Kotlin, Scala, Go, and Ruby, and the technology is called Slang, which is Sonar language. Uh, you might think that this is a great solution. So now we write only rule once, and then it is present in 4 languages. But of course, this approach has some pros and cons. So the pros. Firstly, indeed, you write one rule and it's available in many languages. Another interesting pro that you can adopt new language really fast. So if at one point somebody asked me that we need to support Clojure, we just need to write a converter for Clojure, and then this language will, out of the box, have 40 rules enabled. And I think that's it about the pros. What are the cons? Firstly, maintenance. Maintenance was really difficult because we have to sometimes languages evolve, we have to adapt, we have to add new features of the language and support them, and sometimes we need to make some changes to intermediate representation, to slang, and sometimes this change triggers bugs on other languages. So it happened that some new features in Scala could cause a Ruby plugin or Go plugin to fail, uh, which makes maintenance much harder. Another problem is rules precision, because like it's intermediate representation, we of course have to cut some branches, and the result of the reporting is not really best. So there are a lot of things that we cut, and for Kotlin there were things like objects, extension functions, companion objects that we just ignored because of the way how Slang is implemented. Language specific rules. Of course, if you have to cut some branches, it's harder to implement specific rules for syntax of a specific language because we just don't have enough information. Testing. Now you have to test single rule 5 times, and semantic. So all this was just about the syntax rules. This approach had no semantic, and that's why we could not report issues that had to resolve some variables, that had to resolve some types, and that was really like big limitation for us. So we faced these problems with Kotlin, and that's how we get to the why we needed to do something with Kotlin. So why we needed to do something with Kotlin? Firstly, you cannot we all see that popularity of Kotlin is growing really fast. So we should be like compatible and support Kotlin. Then our users actually gave us a lot of feedback that they want more features, more rules on the Kotlin. They're using it, and Sonar is not great in supporting Kotlin. And then we wanted to use the language in our products because for now almost everything is written in Java, and we face some limitations, some not optimal syntax, and we wanted to use Kotlin in some places. And of course, we needed some static code analyzer for our language. From the company, from the product point of view, we also wanted to support Android and security rules better. And Slang was very limited and was not satisfying our needs. If we continue work with Slang, we could not do this. So we had to find something else. That was time for Sonar Kotlin 2.0. This is what we had previously. You remember I showed you this picture, this scheme. This is what we wanted. We wanted to get rid of the intermediate representation and run all the rules just on the Kotlin uh, tree. What was the problem? The problem was that we already had like 40 rules implemented on the old tree. We had some engine, and it's not like writing everything from scratch. We had to somehow agree these two technologies. So this is what we implemented in the first iteration. In the first iteration, we still continued working with Slang for the old rules, but all new rules were working on the native Kotlin tree. So the result was actually combined of the old rules and new rules. It worked, of course, but of course we knew that eventually we want to get rid of Slang part, so we marked it as a technical debt, promised ourselves that we'll get rid of it, and we actually did it. So we rewrote all the part that was going through Slang to Kotlin native ST and just removed that part. And believe me or not, that was one of the happiest day in my life, removing this part. So I'm talking a lot about Kotlin AST. Let's think about and go a little bit deeper to discover what it is. So when I'm talking about Kotlin AST, there are three possible variants, maybe more, but three most commonly used. First of all, it's program structure interface. It's an interface coming from IntelliJ that is a Kotlin compiler kind of built on. And if you ever added a support of a language into IntelliJ, you probably used it. And that was actually one of the parts already used in our existing analyzer. There is another opportunity, another possible solution, which is front-end intermediate representation. It has better API, better support for semantic. There is one tiny little problem. It's not yet ready for production. And if you ever heard about Kotlin K2, this is about it. So this is going to be finalized in Kotlin 2.0. And there is a third option, Unified AST. This is actually a third-party project that represents some unified AST for Kotlin and Java. It has a little bit worse precision because you have to have unified tree for Kotlin and Java, but gives you more benefits in terms of interop. And this technology is actually used in Android Lint. So knowing all this, we created some sort of a comparison table, and you can definitely see that there is a winner. We decided to still go for program structure interface because we were already familiar with it. It was production ready and gave us pretty nice precision. But of course, it comes with some cost. There are some things that are wrong with program structure interface. First of all, it's nullability hell. As it's designed for the IDE, and in IDE, you're actually typing and you might not finish your sentence, you might have some errors, parsing errors. There is no guarantee that things are not present, that are always present there. That's why almost everything is nullable here. And you know, like in Kotlin, nullability is a part of a type system, so we actually shoot ourselves in the leg by relying on it. What's the problem? Let's imagine we have a binary expression. And in binary expression, if it's parsed correctly, you should always have right and left. But unfortunately, Kotlin compiler resolves right and left as nullable. While in our case, in case of our analyzer, if they are null, we could not even get into that function. So how to deal with this? First possible solution could be to use some safe calls. And for example, calls like let. Here you have nesting, and if it's just two variables, it looks okay, but if there are 5, 6, 7, 10, it gets worse and worse and reduce the readability. It's hard to debug, hard to actually work with. So we were not satisfied with this approach, and we tried to think about something else. Another possible solution could be to use Elvis operator and just return if something is null. What's the problem here? Here we introduce the path on your code that is unreachable, and you screw up your coverage, and you basically lose a little bit of a control because in a year you'll question yourself whether this path is just not tested or this path is actually unreachable, and it's still hard to work with. So we need something else. Another possible solution, just use non-null assertion. They were designed for it. But every time I use non-null assertion, there is a tiny little voice inside me that is telling me, please don't do it. That's something wrong. And yet, that's also not satisfying us. So there were we had to think, we had to have a lot of fights, arguments with our colleagues, and finally we figured it out. So we decided that we'll still use non-null assertion, but every time we do it, we add the comment why with an assumption why we think that it's never going to happen. And it already paid off. We already faced some issues where our assumption was wrong, but because we had a comment, it was pretty easy to fix it. So if you also face a problem like this is a life hack. You can use it. But that's not all of the problems with C. Another problem is lack of documentation and naming. This is my favorite question that I actually ask some Kotlin compiler maintainers and some people from JetBrains. What is KT named function? Like sane people in my team, we believed that KT named function is a function with a name. So when we actually implemented a rule called bad function name rule, we used this fact. So we visited named function, all the named functions. We assumed that name is always present, put non-null assertion with a comment, and reported an issue if name matches some regular expression. Then we have an example. This is an anonymous function in Kotlin. Function is anonymous, it doesn't have a name, so we believed it will never actually step into this function. But when we executed our rule on this code, we got null pointer exception. Why? Why we got null pointer exception? Because we actually entered into this function, went to the line where we put f.name, because function is anonymous, name is null, and non-null assertion triggers null pointer exception. So our assumption was wrong. And after some investigation, after some talks, we figured out that KT named function is actually a function declared with keyword fun, and it has nothing to do with the name of the function. And there are a lot of gems like this in Kotlin compiler. Another interesting point are compiler diagnostics. You know, compiler can generate some warnings, errors, infos for you, and it would be a shame for us not to reuse them and show them to you. So in order to implement deprecated code used rule, we actually reused the compiler diagnostic. It worked like a charm, except that one moment we had a user report with an example, uh, which had deprecated enum and wrote index out of bounds exception. It wasn't clear why index out of bounds exception should happen, but it actually happens here. So we basically tried to report on something that does not exist. After some investigation, we realized that when you actually write entry of the enum, you're calling constructor and you're actually calling constructor my enum implicitly. You don't mention it. And when you put deprecated annotation, you are not only deprecating the class, you're also deprecating the constructor. So basically, the constructor is deprecated and you're calling it, but there is no representation in the source code. So we tried to investigate what others are doing with these situations. And in IDE, basically, they have a workaround and they just highlight the opening parentheses. So we decided to be consistent and highlight the same. But be cautious, sometimes there are actually elements that have no representation in the source code. So knowing all these problems and a lot of more problems with PSI, we still plan to switch to front-end intermediate representation once it's ready for production and we are going to be familiar with it. So now we are investigating playing with it in our playground, and soon we are going to switch to it. So We fixed a lot of bugs, improved, rewrote our 42 existing rules. We dropped the Slang tech debt, and we released our first release of Sonar Kotlin 2.0. We were extremely happy about that, and we expected that the feedback would be like this. But in reality, feedback was sort of this. So what happened? Once we released it, we got a lot of users actually reporting that our analyzer started being very slow, and we had some performance degradation, and sometimes we even hit out of memory. Unfortunately, our internal tests didn't show that, so we tested on different projects and everything worked fine. And for some reason, it was not working that well for our users. So what we usually do when we have problems like this, we gather a meeting. So we gather the meeting, we try to discuss what we are going to do with the performance degradation because we needed to fix it and to do it pretty fast. The first idea, let's do parallelization. Another one suggested maybe we should add caching. There was a guy who actually suggested maybe we should find a bottleneck and fix it. Of course, we threw him out of the window, but then we realized maybe that's not the bad idea. Let's try to find the bottleneck. And the first candidate was commented out code check. So, um, as far as I understood, you usually write code, and sometimes there are people who comment code. And we have a rule that highlights a code in comments and says that please don't do it. So basically, you can see that if comment contains code, we report it as an issue. If it's just a single comment, we report no issues. So how it worked? Before 2.0, we actually went through all the comments and we parsed them. If parsing was successful, we report an issue and assume it's code. If it was not successful, we assume that it's not a code, so everything should be okay. What's wrong with comments like this? If you try to parse comments like this with Kotlin parser, you actually report it as a code because world could be considered as an infix function. And basically in Kotlin, every combination of 3 words and more could be considered as infix functions. So will be parsed correctly and will report a lot of false positives, which is not what we wanted. And before 2.0, we had to have some ugly workaround to filter out issues like this. But after 2.0, as we had some semantic information, we decided that we can fix it better and write it better. So we're still going through all the comments, but instead of just parsing, we are actually compiling it. So we are parsing and generating semantic information. For the cases like that, it worked, but there was tiny little problem. It became slow, like drastically slow, like completely slow. And we had a bunch of other problems. First of all, we stepped into a few compiler bugs because we are triggering compiler on the thing that is not supposed to be compiled. Also, there could be code with mistakes, and now we can falsely report it as a false negative, like don't report there where it is code. Also, code might not be written in Kotlin, and we still don't report it. And of course, slowliness. It became very slow, so a lot of users, especially Android users, started complaining. And we needed to figure out, we needed some solution. And because we had a lot of pressure, we find out a solution. We're not proud of it, but we decided to comment it out code rule. So we simply suddenly ignored this rule. It never triggered. And for a year, we had 0 complaints about the rule. Then I was back to talking at the conferences. I started talking about this at the conferences. So several months later, we got first complaint. And then we decided, okay, maybe we should rethink. And we decided to have some heuristics algorithm that actually is trying to have a probabilistic algorithm that tries to answer a question whether it looks like code or no. We are trying to find keywords, some Kotlin specific structures, lambdas, camel case, and then if the probability that it looks like code is pretty high, we try to parse it. And for now, we found we had no reports about false positives here, but of course it's heuristics and it could fail. So I can challenge you to find some false positives or false negatives and report it to us. Yeah, and now I'm going to talk to you about the most favorite hated rule, which is unused import rule. If you want to implement unnecessary imports rule, probably you'll have some sort of this algorithm. Firstly, you collect all potential references in your code, and then you filter out everything that is referenced in. We filtered out everything that is referenced in KDoc, filtered out references in code, array access imports, and all the remaining imports are considered as unused. Looks smart. And then we forgot about one tiny thing like companion object. For companion object, the referenced name is not actually the one that is imported, and that's why we had false positive. It was pretty easy to fix because the importable name is companion, so you can just check if the importable name is companion and check the reference of the parent. But then we realized that we also forgot about named companion object because some people they not just use companion object, they write it with a name. Okay, we had to investigate it. We found out that in not that well documented Kotlin compiler there is a specific function is companion object, so we fixed it. We thought, okay, now that is the end and that's working now. But no, we had another problem. Another problem was with unresolved imports. What's it? Sometimes in static analysis, we have missing information, for example, binaries or libraries. And because of that, we could not resolve the types or some other variables declarations. And some imports could be unresolved. And because of this, you might face false positives while they're actually used because my package my class was just not found on your class path. Um, so one easy solution was to filter out some unresolved imports because in this case we cannot say nothing and cannot be more precise. So we just filter them out, not to report you false positives. Then we'll face an issue with delegates. So some people write delegates, and here the problem is that what you see in the code of when you use delegate, it's just by keyword, but what you see in imports, it's a get value and set value. And that was not really easy to figure out why you have this false positive. And after some investigation, we find out that you can actually get the importable name from delegate references. So we added some fix and fixed this sort of a false positives with delegates. Another reported issue was with overloaded operators. In Kotlin, you can overload operators like contains, invoke, and in your code you can just write in, not in. You can just invoke anything that is not actually a function. And that looks nice in code, but that's a nightmare for static analysis. Why? Because this is how you should implement your operator. This is actually how function looks. It contains and invoke. And this is what you import. But in code, you see just in and not in. After some workarounds, some ugly hacks, we find out how to get referenced name from these operations and find out the operator for contains. So we fixed the false positive with contains, but we still had a false positive with invoke. Why? Because from the syntax abstract syntax tree, there is no difference whether you invoke something with invoke operator or whether it's just a function, because for us everything looks similar. So we had to visit all function calls, to actually understand if they have invoked there or no. That was not optimal, so we decided to have some sort of a lazy optimization, and we only visit all the calls in case if there is at least one import with invoke, because otherwise it would be just unnecessary step. So okay, we fixed import with invokes. We thought that that's it. We finally had an idea on necessary imports rule, but no. Another report was coming with an incomplete semantic. There are some cases when you have two functions, for example, two functions in different packages, maybe in different libraries. One is in your class path, in your actually built classes. Another one is some external library. And for example, some people, they actually try to tune properties for some reason, and put, for example, some property as Sonar Java binaries as empty. So what happened actually? Happened that the function package.a.do something was not present in the class path, while the other function from external library was present. So our do something was actually resolved to the wrong one. That's why we cannot say that we had an error because function was still resolved, but we still had an unused import of package A do something. Unfortunately, in this case, we can do nothing because we cannot say whether it's just your real mistake and import is really unused, or whether it's a compiler mistake and it resolved something in a different import. So I ask you very much, please don't tune the properties that are auto-generated if you don't know what they're doing, because the result is unpredictable. Okay, we noted this problem. We thought, okay, finally that's it. We're not going to have any other report on unused import. And then Java 16 Plus arrived and people started using it. So recently I had a report with a person who is using toList extension function on stream. And while it's definitely used, we report it as an unused. After some investigation, like we found out that there is an extension function in Kotlin on stream since Kotlin 1.2, but starting Java 16, there is also toList native function in stream. So if you're in Java later than 16 or later, you're basically Kotlin compiler resolves toList function here to list from stream instead of to list from Kotlin. And that's why the issue is reported as unused. But the problem is that the user actually used Java 16 just to build your project, but targeted Java 11. So basically, this toList function from stream should not be visible. Unfortunately, in our analyzer did not understand this. Just thought like if runtime Java version is 16, probably the bindings, the functions, and API should be also from Java 16. Fortunately, we know how to fix it. We noted this problem and the fix is going to be soon. So don't worry, we're going to fix it. And of course, that's not all the problem that we faced on our way. But it sounds like a never-ending story because all the time we cannot ever reach a perfect state of static analysis because we are trying to solve a problem that is proven to be unsolved. We can only reduce false positives and false negatives and react to your feedback. So we are almost at the end of the presentation. Let's a little bit talk about our achievements. First of all, we improved the precision. We just implemented 108 new rules. And we had 13 new releases. And we have rules for regular expressions. We had rules for security, updated external linters mapping, and now our community handling is very fast. And there are a few takeaways that I want you to take from my presentation. First, now Sonar supports Kotlin, so if you use Kotlin, you can use our tools to analyze your code statically. Another point that static analysis for Kotlin is always fun because of the features, sometimes pain, but usually fun. Be active community member. Most of the issues reported were reported by the community, so we try to react on your feedback pretty fast. And if you want us to improve, please report. And rewrite if needed. You've seen like our initial approach didn't satisfy our need, so we were not afraid of rewriting stuff, and we benefit from it a lot. There are some thanks. There are people behind me that actually presentation and with actual Sonar Kotlin. There is initial squad and my team behind. So that's it. Thanks a lot. And if you have some questions.
Thank you, Margarita, for this highlight and trip to Kotlin world. I think we need to give some more time to the audience to write their questions in Slido. So we are waiting for your questions here.
Mhm.
And maybe in the meantime, I should thank you for the times in the past when you was among organizer of Kotlin Night in 2019 and great Jack Daniels party after party, and it was great time and great Kotlin event in Kiev. I'm personally thankful to you for this, and I have small question. Maybe you can highlight some differences between Sonar Cube editions and is Sonar Kotlin free? So.
Yeah, our Kotlin Analyzer is available in Community Edition. So it's basically free. If you know, in Sonar Cube, we have Community Edition, which is free. We have Developer Edition, which costs some and stuff and uncovers some features like taint analysis, I guess, some analyzers for languages like C++, Objective-C, and so on. And there is enterprise and data center editions, but they are more for big companies with uh, when they actually need to host their Sonar in the cloud with many instances. So usually for small companies, it's more about developer and enterprise edition.
With companies with
And
big
Kotlin is
budgets.
free.